Hello, everyone. Hope you all had a fantastic week, the QCon conference in New York. CapitalOne has been sponsoring this conference for the past several years. And personally, for me, this is the second visit. Last year, I was here manning the booth for CapitalOne. If curiosity got the better of some of you in terms of thinking, like, what does a large financial institution have anything to do with serverless architectures, then you definitely are in the right talk. My name is Srini Uppalapati. I'm a vice president in the consumer bank engineering team here at CapitalOne. Within the bank, me and my teams are responsible for a few different things when it comes to the software delivery portfolio. First and foremost, all things related to payments, money movement, fraud, building real-time decisioning platforms to prevent fraud, DevOps, and then managing the public cloud office for the consumer bank. Consumer bank engineering team is primarily spread across 3 sites. We have an engineering team in McLean, Virginia. We have a pretty large engineering team in Delaware, Wilmington. And then lastly, the New York office. And the New York office in 114 and 5th Avenue is quite fantastic. And we have tremendous focus in terms of hiring top-notch engineering talent in New York in the upcoming year. The other interesting thing about our multiple site strategy is we have pretty tight collaboration between product and tech in each of our sites. And we have a lean towards staffing cross-functional teams so that engineers can build awesome digital experiences for our customers at each site, from soup to nuts, without dependency from other sites. CapitalOne is one of the top 10 largest banks within the United States. We serve millions of customers across the country, offering a range of financial products from credit cards, checking and savings accounts, auto loans, small business and commercial accounts as well. I'm going to kick us off. In my portion of the talk, I'm going to kind of lead us through the existing architecture of CapitalOne systems, then talk about the increase in growth of our customers across our various digital channels, and what kind of challenges it presented itself, and then kind of let the context to that, and then lead us through this project or platform that we have built called the Transactions Hub, with a lean towards serverless architectures, and what kind of problems it alleviated in doing that. And then I'll transition my talk to one of my lead engineers, Kiran Satelli, who is going to build upon additional use cases in the bank that we started to, again, leverage serverless architectures based on the success we had with the Transactions Hub. So let me dive in directly. So traditionally, the retail bank within CapitalOne has been powered by a large monolith mainframe system. When you think of a large monolith mainframe system, it's pretty much a bank in the box. What I mean by that is this mainframe system has customer information, transaction information, account information. It's pretty much the ledger that generates taxes and also statements. The traditional channels of mobile, web, as well as the branches where our customers walk in to service their accounts integrate with our modern RESTful API platform that CapitalOne has heavily invested in the recent years. This RESTful API platform, in addition, we also have our own API gateway internal to CapitalOne that secures these APIs for clients to securely integrate with them. And we also have an external dev exchange portal that exposes these APIs to third-party merchants, and also a dev exchange portal for our developers to play with our APIs. In addition to this new RESTful API layer, we have a legacy SOAP layer that interacts with this mainframe system. Now, the channels talk to the APIs, then to the SOAP layer, and then eventually to the backend mainframe system to read and write information. In a nutshell, the large financial institutions across the whole world mimic this architecture today. Probably 10 years ago, 15 years ago, this architecture was fine. But with the advent of cloud, DevOps, CI/CD, and new digital experiences that we are building for customers, we have seen some significant challenges with this architecture. In the last 2 years and more, CapitalOne has made significant investments in their mobile platform, both iOS and Android. And our customers have told us loud and clear how much they relish servicing their accounts on our industry best rated mobile application. Basically, we are seeing a steady growth in consumer traffic, especially the new accounts, and how they are servicing their financial accounts using our mobile application for CapitalOne. I have the good fortune of collaboratively working with a brilliant product team at our multiple sites. Together, product and tech are collaboratively thinking about innovative digital experiences to make the financial lives of our customers much better. There is a problem with this. The newer RESTful APIs, the newer front-end digital experiences we are building, all these applications and services are being deployed continuously into the cloud using robust DevOps CI/CD practices. In some cases, we deploy multiple times into production in an audit-compliant way, which is unheard of in a large financial organization. When you think of the large mainframe system behind these services, as I mentioned, it was a bank in the box. It becomes a nightmare to push any kind of code changes really relatively faster. And the challenge there really is a large regression manual testing window anytime you touch anything because of the kludgy dependencies and the web of dependencies. So suddenly, we have a clash of the modern infrastructure that is getting continuously deployed into the cloud, and then the legacy mainframe infrastructure that cannot move as fast. The net result, when you think of the kind of products we want to ship and place them into the hands of our customers, we are severely challenged when it comes to speed to market. So I'm kind of walking you guys through in terms of the challenges that we as an organization started to face with some of the legacy architectures clashing with the modern cloud DevOps architectures. In addition to that, we are offering some really interesting digital tools for our customers in the mobile platform. There are quite a few of them. I would like the time to share a couple of them. One of the foremost thing being the Zelle person-to-person money movement experience that makes it extremely easy, fast, and secure for our customers to stay within the mobile application app for CapitalOne and seamlessly send and receive money for their family and friends who could be banking with other banks. Our customers love this Zelle application. And I'm pleased to announce that my engineering team has built a fantastic microservices architecture for all the services that power up the Zelle experience. And this is one area where, in some cases, we deploy multiple times each single day into production, and we are able to release these experiences frequently to our customers. Similar to that, our card customers today enjoy a feature called Second Look, where CapitalOne systems monitor the account activity of a particular customer and proactively alert them through email alerts as well as in mobile application notifications if we notice any transactions that we think are suspicious. Proactively letting the customers know that they should take a second look at these transactions because, after all, it is their money. And it is an instant hit with our customers, too. So these are few specific examples of digital tools. We are continuously innovating with our product team and offering these experiences to our customers in our digital channels. So a combination of steady increase in growth in our mobile channel and other digital channels in conjunction with the new digital experiences that we are offering for our customers. During peak volume traffic, Thanksgiving as well as Christmas time, we did see degradation in performance of certain services that are reading and writing information from the mainframe systems. And in some cases, we have seen stability issues too. Now, one option on the table was to throw more money against the monolith mainframe system, make it more resilient, increase the CPU performance cycles, and make it faster. But that's necessarily not the direction we as an engineering team wanted to go. Anyhow, that was really the trigger for us to really remediate some of the challenges that we have been facing. And the biggest thing to solve for in this situation is, like, where exactly do we start? When I talk about a bank in the box, where exactly do we start? On closer introspection and analysis, we figured out that 80% of the read queries against mainframe were all hinged against customers trying to retrieve their financial transactional data. And that was our biggest opportunity, and that gave us the focus needed. And we set on to establish a project or a platform called Transactions Hub in the cloud. And our high-level goals were to cache the customer's transactional data, billions of transactions, securely into the cloud, migrate the traffic off of the mainframe system to the cloud, and then ease the pain, make it such that it performs faster, but more importantly, resilient and scalable for additional growth as we continue to build customer-friendly products and experiences. So based on what I spoke so far, when you think about the solution that need to be developed or built, there are few major work streams. First and foremost, what data store do we choose in the cloud? And the goal here is like billions of customer financial transactions must be stored in that data store. We decided to go with DynamoDB for a few reasons. First of all, it's a managed service, and we really like that about DynamoDB. We want fast response times when it compares to reads against the data store. And DynamoDB, with its cached solution that is on offering, definitely meets the mark on that. But more importantly, the ecosystem of DynamoDB, Lambda functions, and DynamoDB streams was really enticing for us because strategically, we had a need to stream transactional data to upstream applications to open up new digital experiences. For example, we can start generating statements in the cloud. And then we can think about real-time fraud detection as another example. So there are so many plethora of use cases that would open up once you unlock the transactional data from mainframe systems and make it available for readily to be consumed in the cloud. The next important work stream is billions of customer transactions. How do we bootstrap or prime the data from the mainframe system and make it available in DynamoDB? Another critical work stream is how do we keep both the data stores in sync near real time and ensure that there is data integrity between the mainframe system and DynamoDB in the cloud. Once you solve for these things, the next thing would really be building a new GetTransactions API in the cloud that connects to DynamoDB, securely reads transactional data, and presents the data outward to all the channels that are looking for customers' transactional information. The final icing in the cake is to really migrate customers' transactions that is currently reading the data from mainframe system in a safe and secure way, pivot it, all the read traffic to DynamoDB, and alleviate all the performance issues that are caused by going against the mainframe system, not to mention the cost associated with the CPU cycles and the number of calls that goes to the mainframe system itself. So how did we go about solving for these major work streams? So we put together a top-notch cross-functional engineering team and empowered them to solve for these work streams by establishing certain well-defined success criteria or acceptance criteria. First and foremost is speed. The new service that retrieves customers' transactions must perform much faster and better than the legacy API. And the legacy API performance numbers and the data associated with it were available for us, so we knew what response times that the team was going after. The next significant thing is data integrity. Given that we are a reputed financial organization and we are talking about customers' financial information, there is little room for any kind of compromises when it comes to data integrity. And we want to ensure that the data quality is true with the source system. And lastly, security. We need to ensure that data is properly encrypted at rest as well as in transit, because we are talking about taking customers' transactions from the mainframe system and making it readily available in the cloud. So we embraced the CQRS pattern. It's a pretty industry popular pattern. Command query responsibility segregation pattern. In this particular pattern, there are two data models, one data model for all the read information and one data model for all the write information. So when you think about how CapitalOne customers transact and service their accounts, they could be depositing a check, they could be swiping their debit card, or provisioning their debit card in a point of sale and tapping it through their phone. And all these transactions flow through various networks and hit the mainframe system, and that's where your write modal is. And then we establish a mechanism to replicate and cache these transactions within near real time in the cloud, and then you have all the channels reading customers' financial transactions from the read data model. In this particular slide, I'm going to walk us through the high-level logical architecture diagram for Transactions Hub. Now I've mentioned the various work streams, the high-level architecture pattern, and then the serverless components within this through which we solved for this. Within the mainframe system, we had a COBOL program that basically extracted the customer's financial transactions, writes all those financial transactions into a file. This file securely passes through CapitalOne's internal gateway and gets FTP'd into the S3 bucket, and the file is stored there in fully encrypted form. The moment the file arrives in the S3 bucket, we have an SNS notification that gets relayed indicating that the file has arrived. There is a Lambda function that is subscribing to this notification, and what it does is basically inserts the state of the file into an RDS instance, indicating that the file has arrived. We also have a CloudWatch trigger rule that actually triggers another Lambda function, which reads the state of the file in the RDS database, and then it basically invokes this EC2 instance and a Spring Batch application that runs on this EC2 instance. Basically, it spins up the entire stack based on the file being arrived, and this Spring Batch application connects to the S3 file, reads each transactional record, and then we use client-side encryption with region-based KMS keys to encrypt each record and safely and securely save the customer's financial transaction into DynamoDB using DynamoDB's API. This takes care of the bootstrapping or priming of files and data and catching up DynamoDB to sync up into the same state as the data in the mainframe system. The next big work stream is how do you keep both these data stores in sync? And this is where we leverage a messaging system. So we have an existing IBM MQ infrastructure that is connecting to the mainframe system. We have created 4 new remote queue managers, and then there is a COBOL program on the mainframe system. As each transaction hits the mainframe system, it puts those events seamlessly onto the queues. Then in the cloud, running again on an EC2 instance, we have a Spring Boot application. This is pretty much an MQ listener that is listening to the transactional events that are arriving from mainframe system, and then again, it encrypts each of those transactional events and successfully ingests them into DynamoDB. Now that the data is available both real-time and in batch mode, all the client channels can now seamlessly access this data through our internal Dev Exchange gateway by calling an API, the GetTransactions API, that we again have built and deployed into the EC2 instance running in the cloud. And this connects to DynamoDB, seamlessly retrieves all the transactional information, and presents it to all the channels. So you can see that about 12 months ago, we have incorporated this solution by using a combination of EC2 instances, certain services, Spring Batch applications, and Lambda functions to build this platform called Transaction Hub and make it readily available for our various channels to consume transactional data. So within CapitalOne, there is tremendous rigor within the engineering teams when you think about operational monitoring. We leverage New Relic and Nagios to monitor our APIs and other applications. What you are looking at the screen is a monitor for our GetTransactions API. I'm pleased to announce that the entire transaction platform is live in production for the past several months. And the new API is performing much, much better. It clocks an average time of about 50 milliseconds during peak volume traffic. And I'm humbled by all the hard work done by the team that we are in a very good spot when it comes to alleviating some of the pressure and cost implications when it comes to depending on the mainframe system. In addition, we also have business monitoring by leveraging Elasticsearch and Kibana dashboards. So on the screen on the left-hand side, you're seeing the Kibana dashboard monitor for all the batch data ingestion for every single day. And you can see that we are able to ingest successfully millions of transactions from the mainframe system going into DynamoDB. On the right-hand side is a Kibana dashboard monitor that actually shows the real-time ingestion coming through the messaging infrastructure. And this kind of business monitoring is giving us the transparency to let us know at what hour during a given weekday, how much traffic can we expect, and how long is it taking for the destination data store in DynamoDB to catch up. So we today have an average lag of approximately 5 to 6 milliseconds for near real-time transactions to be caught up. So this brings to conclusion my portion of the talk. And I'm going to hand it over to Kiran Satelli, who is going to walk us through how our team kind of built upon the success of Transaction Hub to basically incorporate more serverless architectures to solve for similarly account-related information, statements, email generation, and few other things, in addition to also talking about other learnings that we had when it comes to leveraging serverless architectures in general. Thank you so much.
Whoa, whoa, whoa. Thanks a lot, Srini, for giving such a detailed overview of Transactions Hub. Well, I just wanted to say that right now, Transactions Hub is live in production from last couple of years, and we have been serving millions of transactions every day for our customers at a lightning speed. If you might have just seen a couple of slides back, you have seen 50 milliseconds response time for almost like 3 billion transactions items that we are storing in DynamoDB. That is phenomenal. And I just wanted to even say that we are having almost like 13 terabytes of data in our DynamoDB right now. So, well, hello friends. My name is Kiran Satelli. I am a lead software engineer working for core banking platform. And I have even the privilege to say that I was a tech lead for this Transaction Hub. And I was there from the inception of this whole project till when it went live into the production. And as I'm speaking over here, that means the whole project went live successfully, and there were no issues for the financial transactions not to be presented to the customers, and I was not sacked in the company at least. Okay, and after the successful rollout of Transactions Hub, our leadership team decided to build a look-aside cache of accounts data set in cloud. So what does that mean, actually? So they were saying that, hey, we have got all our transactions information in cloud, and we are able to serve the customers much more faster. So what does it mean for taking our accounts data set also into cloud? Because accounts data as well as the transaction data happens to be like 70% of the populations that our mainframe systems were handling. We could have just leveraged the existing pattern of Transaction Hub because it was already proven. But we as a team decided to further enhance upon it. So we decided we actually were targeting towards going more serverless. And a couple of factors that were actually making us to lean towards serverless was the cost and the maintenance of the batch stack. And when you say cost and the maintenance especially is because we are spinning up these EC2 instances on demand, and we are supposed to ensure that we are having the latest AMI patches for our EC2 instances, for which we have to ensure that we are having our CloudFormation templates updated every time with the latest patch. So as part of the new architecture, we completely eliminated these EC2 instances as well as the RDS stack, which were previously used for us to have this processing of data in the batch mode. And we started leveraging step functions, which orchestrates series of lambdas to read millions of accounts data and ingest them into DynamoDB. We are going to be talking more about the step functions in the next slide, but this is how the new Account Hub architecture is going to look like now. So in the previous slide, when Srini actually presented the Transactions Hub, although it was an on-demand EC2 instances, but he was repeatedly using the word EC2, 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 and we thought that, okay, we are spending a lot of money on the EC2 instances. And by that time, serverless was just the step functions and all those things were still emerging actually. So the moment the step transactions hub went live and step functions was becoming more mature, we started deciding to use these step functions, as I said earlier. So over here you can see in transactions hub, the data that is actually getting flowed from our source, as Srini already mentioned, is in two formats. One is in the batch format and one is in the real-time format. Okay, in the batch format, the files are actually generated. This time this is account-related files, and these files are securely FTP to our S3 bucket. And we are actually having a CloudWatch rule that is scheduled to trigger at Lambda, and I'll call it as a batch trigger Lambda over here. And this batch trigger Lambda just keeps on polling this S3 bucket to see if it has received the files. And if it has received the files, it keeps a counter of the number of files that it has received. And the moment it hits a threshold that we have set according to our business requirements, it triggers our step functions. And this step functions goes and calls multiple Lambdas behind the screen, which reads the data from S3, downloads the data from S3, parses the information, and writes the data into DynamoDB. The second channel that I was talking of, which is the real-time messages. So our mainframe sends the real-time messages through our IBM MQ. And we have just followed the same path of having a MQ client created in production on cloud, which reads this message from the queue and writes the data into DynamoDB. So now you can see over here one more difference over here. We are no more using, or we are not having a separate stack of EC2 instances for APIs as well as for the MQ consumer. So we have enhanced even the stack over here to have the ECS. And we are running on this ECS, we are running the API as well as the MQ consumer as two different tasks, just ensuring that we are saving some cost to our bank at least. So I just wanted to know as to how many of you might have used step functions in the real time for batch processing. Do we have any? Perfect. Awesome. So this is a good place for all of us to share our experiences or at least get some learnings from whatever we have learned. So we have written 3 step functions, one at the batch level, one at the file level, one at the chunk level. So the batch level step function, the batch state machine, orchestrates all the steps that are required in processing of a job. What it means is it ensures that all the business requirements are met before proceeding with the job. It bootstraps all the Lambdas by creating the necessary input files, and then it stages all the files and folders for running the job. Once all these prerequisites are met, for each file, we spin a file state machine and wait for its completion. And as you can see over here, the batch, for example, just let's take an example of we are trying to process a batch of 11 files or 3 files over here. So the moment systematics or the mainframe system sends to S3 bucket the 3 files, the batch trigger triggers the step functions, and step function sees that, hey, we have received all the 3 files. It performs all the business functionality that should this batch be run today or was it yesterday's files, and all those business requirements are met. And once that thing is done, as we are having 3 files over there, the batch state machine executes three file state machine executions. And the file state execution, all that it does is it takes a file and it splits that file into further smaller file sets and uploads them into S3 bucket. And once the files are uploaded into S3 bucket, this file state machine executes chunk state machine, and this chunk state machine in parallel. Okay, and the chunk state machine's responsibility is to get the chunk of data and read, encrypt, and write the data into DynamoDB. So this is how we have actually come up with the complete step functions. We are able to completely say that we have a batch job which is purely serverless in nature. Okay, and I just wanted to even share some compute costs that we have just gathered. So we have like 11 files that we try to process every day with almost approximately 10 million information in it, and it runs for 60 minutes, and the total compute cost of this whole thing that I'm talking about is just 78 cents. So which is very, very much phenomenal, and this is just the compute cost that we're talking of, okay? I'm not trying to say anything about the DynamoDB cost. It is having its own cost, but still, okay? So for resiliency purpose, we have our stack spread across both east and west regions. So as Srini has already pointed out that we are using the client-side encryption with region-specific KMS keys, we are constrained to use the new DynamoDB feature of cross-region replication. But as this is a look-aside cache or a CQRS pattern, we are able to write data into multiple regions at the same time. So in case of a region-level failure, that is like if the batch job fails on one of the region, we are able to serve the data from the other region at least, where the data is completely correct. So if you see over here, if the US East one, the batch job fails on the US East one, as we are writing the data parallelly on the US West 2, we are able to redirect our traffic to US West 2 at least. And we are even ensuring that the data is completely synchronized between East and West by having our source system to send the files in case of the batch mode to both the regions as one single transaction. And in case of the real-time transmission, the same message is sent to two different queues as part of the same transaction. When I'm using the word transaction, if the source system is unable to push the file, for some reason, both the files will not be coming to our region, and at the same time, if the message is not being delivered to our IBM MQ, then the transaction will not be considered as the file that message that has been sent from the source system. Now, recently, we have got the DynamoDB has given the support for encryption at rest. And me and my team are actually working on leveraging this encryption at rest, which will help us to stop doing this client-side encryption, which has created the constraint for us to use the cross-region replication. And why we are actually trying to lean on the cross-region replication more is because we have the privilege of working closely with the actual architects of the DynamoDB team, and we are able to influence their product, saying that we want this requirement, we want that requirement, and we know that there is a lot of features that are going to be provided as part of the DynamoDB. So we are actually targeting for improving our application, Account Hub batch application, to start leveraging the client-side, the server-side encryption concept. It is always challenging to monitor a serverless application, okay? So as part of the Account Hub batch, apart from the CloudWatch metrics, we even started integrating ourselves with PagerDuty and Datadog. So once the file state machines, in the previous slides, as I said, once the file state machines executions gets completed, the batch state machine collects the metrics of all the file state machines and aggregates them and sends it as an SNS topic, SNS to a specific topic. And this topic is subscribed by a Lambda function, which parses all the information and creates necessary metrics on Datadog. And as these metrics are made available on Datadog, we are able to create some interactive dashboards, which really help out the development team as well as the product team to make sure that everything looks great. So as you can see on the screen, we are having almost these many records that are inserted on both the places, on east and west. We should make sure that the numbers match over there, okay? If even two transactions or two items are mismatching, that means the batch has failed for some reason. And then you can see the total number of step executions and the total number of step execution failures, and the Lambda function invocations on the east and DynamoDB writes over there. So if you can see over there, when the Lambda, if you see the timing over there, I don't know whether you're able to see it because of the small font size, but we have this batch job that runs early in the morning around 2 o'clock or 3 o'clock. So until that time, the DynamoDB writes, you see that it is actually at the 0K, and during the batch execution, we actually increase the WCUs. Okay? So what we even try to do is, as part of the batch state machine, we are leveraging our AWS Lambdas to dynamically increase the WCUs when the batch job starts and dynamically decrease the WCUs once the batch job is completed. Okay? So I just wanted to highlight that one. And we have created a couple of alerts on PagerDuty, alerts on Datadog, which triggers PagerDuty whenever we come across any errors as part of the Lambda invocations or any sort of discrepancy. Recently, AWS X-Rays is approved pattern for us to use in CapitalOne. So me and my team are even thinking of enhancing our monitoring stack to even include AWS X-Rays for debugging of our Lambdas. Yeah, and you can even see that this is the Datadog dashboard, and the right-hand side, you see an email that is actually generated. So this is the email that my team also receives. So we have subscribed our email distribution list for the topic for which the SNS message, that batch state machine sends the SNS message. So if you can see over here, we are having the total number of files. We see what is the start time, what is the end time. And if you see the settings in the below section, you can see that it is having the WCU high. How much is the high throughput that we are supposed to be giving, which is 50,000 over here. And once the batch completes, what is the throughput that we have to dial in back, which is 10,000 over there. So this is how we just try to ensure that we are having everything buttoned up. This slide shows all the AWS services that Account Hub stack uses. When I'm using the word Account Hub stack, it includes the batch, the MQ, and the APIs. So as you can see, the first row, S3, SNS, Lambda, step functions, CloudWatch rule, all these things are something I can call it as a serverless because I don't need to really worry upon it. They are completely managed services. And in the second row, we are having DynamoDB and CloudWatch and KMS. So these are other services where I don't really need to worry about. The ECS over there, it is still on the EC2 stack. And the reason we are actually, we did a quick POC on seeing what does it mean for us to have our APIs also hosted on Lambdas. But there were a couple of lessons that were learned. So when we are actually having a very high throughput, which is a TPS that we are talking of for the APIs, we really had to weigh in whether are we really getting benefited with having a Lambda over there, or are we having a benefit by having an ECS with an EC2 instance that will just process the. So if an API is having a low throughput, it is always advantageous to have just have the API to be built on a Lambda. And if it is having a very high TPS, like beyond 100 TPS, we felt that it was much more advantageous to have that application to be running on an EC2 instance. But as we are using the ECS over here, we are still ensuring that we are managing our EC2 usage a lot. In the next couple of slides, I'm going to touch upon a couple of other business use cases that were built upon Account Hub in order to serve millions of our customer needs. So the first use case is generating the statement-ready emails to our customers is completely developed on serverless technologies. And the second use case says that how CapitalOne is migrating its legacy APIs to Lambda functions. So how many of you might be receiving emails over here from your respective banks that your statement is ready? I know that everyone deletes that, but still, most of you might have. So what does that statement is ready means? So what it means is Kiran receives an email from his bank, CapitalOne, saying that your statement is ready. I see that, and I have to go into my digital channel, which is either web or mobile, and I see my statement and go through all my transactions. So this is what a statement ready means, actually. So this is the high-level architecture of our statement-ready email. So just like any other banks, we are also sending these statement-ready emails for all our banking customers. And this is a fantastic example of the pattern that we have chosen, because we have eliminated a legacy data warehousing control M job, which even included a couple of manual steps and manual approvals with the completely serverless technologies. And this is how we are actually sending our statement-ready generated emails to millions of our customers. So if you can see over here, just wanted to give a little bit of business use case. So usually the banks don't send the customer-ready generated emails on day one for all the customers, because the customers are millions in numbers. So they try to break it up into 1 or 2 waves, or 1 to 3 waves. So what it means is, like day one, 30% of the population will get the customer emails. The day 2, 30% more will get the notifications, and the last day we'll be getting all the 40% will get the notifications. And there are a couple of reasons over there. We just wanted to make sure that we are not throttling our customer call centers with more customers calling in saying that, hey, why we are having this discrepancy or something like that. So this is more like a business use case wherein we had to go in a couple of waves. But why I had to give this context to you is that we try to store this information as part of our RDS, wherein if Kiran is going and querying an RDS data store, I'll be seeing, if I'm saying like it is broken up in 3 waves, I'll see 3 records over there which says that 30% of the population on this date the emails has to be sent, 30% of the population on this date it has to be sent, and 40% of the population to be sent on this date. Why I had to set this context is that will give more overview of this whole flow. So we are having a CloudWatch rule that is scheduled to trigger a Lambda, and this Lambda is triggered every day. And the responsibility of this Lambda is to go and check this RDS data store to ensure that is this the day that I have to send the emails. And if it is that day that the emails are supposed to be sent, then it tries to read all the customer information from S3 bucket, which is another bucket, and it downloads all the data of that customers for the 30% of the population, and then it generates, it even fetches all the necessary email templates that are supposed to be sent to the customers. It aggregates all this information, writes it into a separate file, and uploads it into S3 bucket, a different S3 bucket. And this S3 bucket is read by another app, which is called as a direct send app, which reads all the information and just sends this emails to our customer. So now you can see that we have completely eliminated a data warehousing control M job with completely serverless technologies, and all these things happen in the very first 1 week or 2 weeks of every month. So this is pretty interesting use case I just wanted to share. The second use case is I just wanted to illustrate that CapitalOne is actually trying to migrate most of its business legacy APIs from APIs that were actually running on the EC2 instances to Lambda functions. So this is the architecture of an API called getStatements API, wherein given a customer number, we try to say these are the list of statements that you are having. Okay? So as you can see in the diagram over here, the requests are being sent from the digital channel, which is mobile and web, through our WAF layer, which is a secured WAF layer. The requests are sent to our internal orchestration layer, and the requests are then redirected to our internal API gateway. So this API gateway is not the CapitalOne API gateway. It is an internal API gateway which has its own OAuth implementation. And once the request is received to this API gateway, it tries to go and ensure whether the client is authorized and authenticated to call our API. And once the request is authenticated, then the request is forwarded to the Lambda. And this Lambda just takes the customer number, goes and queries the RDS data store, and gets the statement list and sends back this information to the respective channel. So this is how we have just migrated a couple of our legacy applications to Lambda also. So in the next slide, I just wanted to share a couple of our Lambda as well as step function experiences, which I can call it as a learning and best practices. So the first experience is improve the response time with data caching. So I just wanted to make sure that although Lambda is considered to be serverless, but in reality there is a container that is provisioned behind the screen at runtime for a Lambda. And this container is made available for some time. And if you are creating a global level variable, you will be having this global variable accessible at the container level. So if you are going to store any information into the global variable, another Lambda invocation that comes to the same container will have a hook on that respective on that respective value actually. So we have been using this quite frequently for caching our connections with RDS data store, storing the KMS keys. So this avoids us to again go and establish the connection on fetch the details and something on those counts. The second thing, for example, in this code snippet, you can see we are actually caching the database password which is actually encrypted with KMS keys. So every time the Lambda function invocation happens, they don't really need to go and fetch the KMS keys for every invocation. Once the database is, the password is cached, at least until the container is available, you'll be able to fetch the database password for the subsequent invocations. Lambda concurrency, just like any other AWS service, Lambda also has a concurrency, also has a limit that is set at the account level. But there is a typical problem with Lambda. If you don't properly manage your Lambda, one function of Lambda can consume all the limits at your account level. AWS has recently introduced the concurrency levels at function level, at Lambda function level. So we strongly urge you to use that concurrency at the function level, because if you are not setting this limit, then your function can consume all the limits at the account level, which deprives other function to start throttling, which are not even belonging to your application. So just make sure that you are having your function running and you are making other application teams' functions also running. VPC attached Lambdas. So if a Lambda is attached to a VPC, that Lambda gets its IP address from the subnet of that VPC. So make sure that you are monitoring your Lambda, because the Lambda can eat up all your IP addresses. And all these are the real-time experiences that I'm talking of, because we have been really, at least I have been called out many times saying that, hey, just go and make sure that your Lambdas are killed, because it is eating away the IP addresses and the EC2 instances are not getting the IP and they are not able to get spun up. So at least at CapitalOne, we have created a separate VPC for our Lambdas so that we are not getting ourselves involved into the other services like AWS, EC2 or ECS related subnets. Lambda Cold-Start. So a cold start occurs when an AWS Lambda is invoked after a very long period of inactivity, which increases the invocation time. So what we have seen is we can reduce this cold start. At least we reduce the cold start with following these three things. We trim down the code size and its dependencies. We have used a couple of libraries for our Node.js, like Webpack, Minify, Uglify. So these are some of the libraries that we have used, which shrunk our artifact size so small, and there is no magic that is actually happening behind the screen. All that it does is it removes all the unnecessary dependencies which are never being used in your application, and it just tries to do some formatting. It just messes up with the formatting, which shrinks down the whole packet size. And when we did this, if you can see over here, the file size of the bundle.zip is 5.4 MB, and it has been shrunk to almost 82 KB. So what this helps out is the moment this artifact is uploaded, it becomes much faster for the invocation of the Lambda. Keep the function warm to reduce a cold start. So it's always good if you are aware that your Lambda is very inactive. It's always good to create a CloudWatch rule, to a schedule rule to just go and invoke that Lambda at a specific interval periods of time to keep it warm. And we have even seen that allocation of more memory reduces the cold start. And these are the two things that we have lessons learned for. There are many more, but these are something that I wanted to bring it up. So using the retry policy. The state machine can error out during runtime. And the reasons for the state machine erroring out is more like they just try to error out if the definition is wrong or the task or the state is wrong. And why I had to just put this in over here is because there is a feature to have a property called retry to be put at the step definition level, which can have all the exceptions that we can list out, which says that upon hitting these exceptions, just go and retry the whole execution. Because if the task fails, the default behavior, if this retry block is not there, the default behavior is the whole execution is failed. So if you don't want to, if you wanted to avoid the execution to fail, and we just want to get it retried once again, this is how we just followed the retry policy. And keeping the state data lightweight. So what does this mean is that the state, when we are actually passing the information from one state to another state, you can actually pass the data. So just ensure that you are not passing a hell of a data because there is a limit over there which is 32 KB, and just try to send some sort of pointers as against the actual data. So having said so, these are some of the things that we just had the experience. Srini, can you just come and give the closing notes? Thank you, guys.
Folks, I don't want to hold you up any longer. Thank you so much for your time. We had a blast sharing our serverless journey here. I just want to put out a note there saying we are hiring number of engineers at various levels across our sites. Especially in New York, there is tremendous focus to hire mobile engineers. We are also hiring DevOps engineers, architects into my architecture team as well. You guys have seen the LinkedIn addresses for both of us, so you can contact directly any of us. You can also go to CapitalOne website and look at any open positions. We are desperately looking for top-notch engineering talent, and CapitalOne is a fantastic place to work for. Once again, have a wonderful weekend and a fantastic July 4th. Thank you so much.